Let's compare two proportions using a hypothesis test. Hypothesis tests always have the same 4 steps, so I sort of laid these out here. I have my hypotheses, my model, my p-value, and in the 4th step, I have my conclusion. My hypotheses when I'm working with two proportions is always going to be that the success rate for the first group is equal to the success rate for the second group. In this problem, I'm comparing right-handed and left-handed batting, so I have the success rate for the right hand is equal to the success rate for the left hand. This is equivalent to saying that if I take right minus left, it should be equal to 0. Alternative hypothesis, I think I'm better at right-handed than left-handed. Moving this to the other side, this is equivalent to saying if I take the right-handed number minus the left-handed number, I think I have a large number minus a small number. This should give me a positive. So when the time comes to shade, I know this is going to be a right-tailed test. And from the null hypothesis, the claimed difference is 0, which is why 0 is showing up as a center to the model. Now, this null hypothesis tells me one other thing. I'm assuming the groups are the same. So I'm going to treat them like it's just one big massive group and just shove all the results together here to get my pooled success rate. So my pooled success rate, I add the total number of successes. So 30 successes with the right hand, 20 with the left. I was successful 50 times. Denominator. So this was out of 150 for the first, 120 for the second. In total, it's out of 270 trials. So my success rate for this entire pooled group is approximately 18.2% or so, 18.5%. So if my success rate is 18.5% overall, then my failure rate overall is going to be 1 minus this, and 1 minus this gives me something like 81.5% or so. When it comes time to do the model here, I'm doing right-handed minus left-handed, because that's what it looks like for my alternative. My center is 0 because I'm claiming that there's no difference. I'm going to test to see if that claim is reasonable. And I'm going to take my pooled success rate, 18.5%, times my pooled failure rate, 81.5%. And I'm going to divide this by the number of samples for the first group. There are 150 samples for the first group. I'm going to do exactly the same thing for the second group. And I'm going to divide by 120 there, the size of the second group. This tells me how much deviation I should expect in groups of 150 compared to groups of 120, assuming there is no difference between those groups. So in this case, typing this into my calculator, I end up getting a standard deviation of 0.048 or so. For the p-value, I'm going to draw the curve for what we have thus far. And then I'm going to compare the claim to my data. So the claim is that there's no difference. And I'm counting on my curve by about 4.8%. So this would be having the right hand be better than the left on this side of the curve. This side of the curve is the left hand better than the right. And in the center, there's no difference between them. My p-value is the likelihood of my sample data or more extreme if the null hypothesis is true. Well, my model name tells me how I'm doing the subtraction. I'm taking the right hand minus the left hand success rate. And this is where I compare each of those individual numbers. So I had that 30 out of 150 for the first group, and I had the 20 out of 120 for the second group. The symbol I put here, that determines how to shade, and it's coming from the alternative hypothesis. I'm testing for greater than here. I'm going to type this value into my calculator to see where I should be putting that thing on the curve, and then I'm going to find some z-scores and look them up. So when I do this, I get 0.033 repeating for that number. So my sample difference is here. It's within 1 standard deviation. So when I shade this thing in, this is a sizable amount of the curve. I'm going to have a pretty large p-value. So let's find the z-score by taking our value minus the center and dividing this by the standard deviation. This is how I always find my z-score. My sample value is this 0.033 repeating number. The center of my model was 0, and I was counting by a standard deviation of about 0.048 or so. When I type this into my calculator, I get a z-score of about 0.69 or so. I'm rounding as I'm going through this. If you use more digits, you might end up with a more accurate z-score than what I have. Or you could even leave things as fractions. You don't even have to round at all here. I'm going to look this up in a normal table. And I have a positive z-score. And that z-score was 0.69. So I'm going to go to the 0.6. This is how my z-score starts. 9, that's the last digit of my z-score. And I'm going to see where these things meet in my grid. It looks like I have a table value of 0.7549. If my picture was shaded to the left, this would be my p-value. Since my picture is shaded to the right, my p-value is going to be 1 minus this table number, which gives me a really large value of 24.51. For my conclusion, let's compare this p-value to a neutral alpha level of something like 5% or so. This is larger than my alpha level. If your p-value is low, your null must go. If it's large, you fail to reject the null hypothesis. If you fail to reject the null hypothesis, you don't have evidence of the alternative, so I do not have evidence that I'm better at batting with my right hand. So I don't have evidence that there's a statistically significant difference between the two groups. Again, the process for this: step 1, hypotheses; step 2, model; step 3, p-value, where I compare my sample success rate to the claimed success rate of 0. I find my z-score by doing value minus center over standard deviation, and then I look that thing up in a table, or I can use my calculator or GeoGebra. In conclusion, I compare my p-value to my alpha level, and I either reject if it is smaller than my alpha level, or fail to reject if it's larger. This is one of the few situations where you have to do this weird step at the beginning where you pool your success rates. And the only reason why I'm pooling here is in that null hypothesis, I've said my first group and the second group are indistinguishable from each other. So if I'm claiming that the two groups are the same, I'm not really seeing this as a one group or two group thing. I'm just seeing this as one massive collection of data. So I'm going to pool whenever I'm comparing with an H-test.